Hello, everyone. Welcome to Flink Forward. I hope you're having a good time here. I know it's interesting to do this virtually rather than all being together in one place, which is always fun. I always have had a great time at Flink Forward, but I think this can still be interesting, and at least we get to do this. Yeah. So my name is Jamie Greer. I have my email address. You should be able to see my slides as well. So I have my email address on that slide, jgreer@splunk.com. So if you want to follow up afterwards, you can feel free to email me there. Yeah, and so let's go ahead and get started. I just wanted to give you a little bit of a background about myself. Again, my name is Jamie Greer. I've been involved in stream processing in some form or another for pretty much probably over a decade. I'm currently working on at Splunk on the data stream processor product. I'll probably say DSP a lot in this talk rather than data stream processor, just so that's what DSP means. Prior to joining Splunk, I also have had some other positions focused on stream processing. So I was one of the founding engineers of the streaming platform team at Lyft. And so I had been, before joining Splunk, I'd been at Lyft for a few years in that role. Prior to that, I was the director of applications engineering at Data Artisans, which is now Ververica. That was a really unique opportunity, and it gave me the opportunity to get involved with people developing Flink applications. I would say literally dozens of companies. It was a great opportunity in that I could help people adopt Flink, map their problem onto the stream processing primitives available in Flink, see the challenges they ran into, feed some of that back into Flink itself in terms of what features we should kind of work on. And operational issues. It just gave me a chance to see a lot of stuff, and that was just a really great opportunity. Before that, I also spent a little bit of time working on the streaming platform team at Twitter, which is where I first came across Flink, kind of in some work we were doing there. And even before that, I worked at a company called GNIP, which was really pre-stream processing frameworks, but the core product at GNIP was also what I would say is stream processing, at its very core. So this was pre-Flink, pre-Storm even. And then before that, I worked on video stream processing and some other things. So I've kind of been in the general area for a while. What I want to talk about today is Splunk's data stream processor product, kind of give you a little bit of a product view so you know what the context is, then go over a little bit of the high-level architecture of the DSP product, and then talk briefly, we have plenty of time to talk briefly about some of the technical challenges and why we have some interesting problems at Splunk. Yeah, let's get started. Okay, so at a very high level, what the Splunk data stream processor is a way to, Splunk in general is all about ingesting machine data into a data platform for customers. The Splunk product has been around for a while, and it's pretty well loved, I believe. But the kind of missing piece in this Splunk offering was allowing people to do stream processing on their data. So if you have, like this view shows, you have all this machine data on the left, and you have the various sinks, especially like the Splunk indexer and Splunk cluster, and that whole product on the right. What was missing before DSP was really the ability to do all of the things we think of as stream processing on that ingest stream between those two things. So that means filtering, enrichment, normalization, transformations, aggregation, masking sensitive data. Essentially, if you can provide in the ingest stream a stream processing platform, it enables customers to do a lot of stuff they couldn't do before. So that's really what data stream processing is. It's essentially bringing a stream processing offering to all of Splunk's customers and giving them kind of access to that ingest stream kind of in the middle between its generation and its ingestion into Splunk clusters. So it's a pretty great product. And essentially, I think of it as like we're really just bringing stream processing to the masses. So pretty cool. In terms of like a little bit more of the product tour, this DSP product has a really great user interface. Its target is to make stream processing very easy for Splunk's end users. And so this is like a screen grab. I'm going to show you a few screen grabs of the user interface, so you can kind of get a sense of like what it's like to use it. So this just shows a very simple pipeline. Read from the Splunk Firehose, which is all of your customer data that you're ingesting, the whole Firehose of it. Do something in the middle, any kind of processing that the DSP product offers, which we covered some of. And then on the right-hand side of this is a sink. So in this case, ingesting to your Splunk cluster. When you're going to develop a pipeline, we try to make it pretty friendly from the start. So it kind of looks like this. It's kind of a wizard interface. This is just a screen grab from actually the product docs. But you have like a whole list of various sources you can start with. Then you have various templates you can choose from, which in a template is just like essentially just a way to kind of bootstrap a streaming job, kind of give you a template to do something similar to what you're trying to do. And then from there, you can parameterize it, customize it, etc. Here is another example of a streaming job that you would build using the DSP product. This is, again, it's not a real job. It's just from the product docs, but this is the actual user interface. This is what it looks like. So you can see there's some source, and then there's a chain of things that you put together that are basically your streaming pipeline. Here, there's a where clause, so that's essentially filtering. Eval you can think of as general purpose projection, and you can do a lot of things with it. Here, there's a stats operator, which is really aggregation. We're writing to S3. We're outputting to a metric system called our SignalFX offering. And we're also ingesting data into Splunk clusters. Here is another screen grab from the product. This is a live pipeline actually running. As you can see here, there's a bunch of feedback at the operator level that we try to give to the user so they can understand their job, throughput, latency, etc. But also this slide shows that there is not just this graphical user interface, but there's also the underlying language that you can use to write these pipelines as well. And you use Splunk's SPL language in order to do that. So if you're a Splunk user, you're probably familiar with SPL. It's the same language that you use to do search over data ingested into Splunk clusters. And you can see it kind of looks like essentially source, pipe, operator pipe, operator pipe, operator pipe. And so you can actually, and then in this case, the final sync is the Splunk index. But the two views, the graphical user interface and the underlying SPL are equivalent, and you can edit either one of them depending on kind of like what your background is. So it's a pretty great user experience. So that's kind of like an overview of what the product offering is for the end user, what it looks like. Now I want to jump into the high-level architecture a little bit. So kind of at a really high level, what you have on the left side here is really just, there's lots of ways that internally at Splunk we call GDI or get data in. There's lots of ways that you integrate with existing systems in order to grab machine data and bring it into the system. So all the things on the boxes on the left are really all the various ways supported by Splunk to do that. This isn't new to DSP. It's just all the ways we collect data. But for the DSP product, eventually we're actually syncing that data. So the first stage is to push all of that data into Pulsar, Apache Pulsar. So we're actually using Pulsar internally as our message bus, if you will. And then once the data is in Pulsar, then we can run Flink jobs that ingest the data from Pulsar and then do the whole processing layer of DSP. So the processing layer of DSP is built on top of Apache Flink. A little bit more detail. So there's, in this diagram, you can see the DSP front end. That's the component that's, generating those beautiful user interfaces I showed you, and also allowing people to write SPL. And, at the end of the day, that stuff gets turned into an abstract syntax tree, and then that's submitted to the backend service. Here it's called the DSP configuration service. I'm going to go a little bit more into that in the next slide. Eventually, though, the output of the DSP configuration service here is actually a Flink job. And that, in the normal way, once you have a Flink job, it gets submitted to a Flink cluster. And you can see, again, data producers are producing data to Pulsar. The Flink job reads data from Pulsar and does its thing. And then the output in this case, this is not the only sync available, but the output in this case is a normal Spark cluster. A little bit more information here. So what's marked the REST API here is essentially the configuration service from the previous slide. Internally to that, there is, so as input, you start with this SPL and then an abstract syntax tree. Internally, there's a type checker. So DSP has its own internal type system. So the first thing that happens is that type verification is completed. After that, there is also essentially a planner, a query planner. So the input to that is the AST, the verified AST. The output of that is going to be essentially a Flink job graph that we should all be familiar with. Once there is a Flink job graph generated from the planner, you're good to go. At that point, it's a Flink job like any other. It's then submitted to the Flink job manager and runs like any other Flink job. It's probably not too different from other kinds of high-level languages where they're compiled into Flink jobs at the end. For example, Flink's own SQL engine would work something like this internally. Yeah. So that's kind of like the very high-level architecture. In this format, we don't have tons of time, but I did want to talk about some of the interesting technical challenges that we're working on. Beyond all of that infrastructure and product we've already talked about, there are some interesting scaling challenges that I've been a little bit involved with and I want to talk about. So there's two dimensions of sort of scaling challenges that I think are interesting. The first is scaling individual pipelines to very high throughput. So I'll talk about a little bit about that. And then second, there is how do you, essentially these other scaling challenges, how do you scale DSP product offering and its underlying implementation, which is Flink jobs, to very high numbers of customers. So I want to spend a little bit of time talking about that. Okay, so the first challenge I want to talk about is scaling for throughput. So, how to go fast. At Splunk, we have some of the highest throughput Flink jobs of anywhere in the world that I'm aware of. There could be others. I just haven't seen them. So for sure there could be. But at least for me, these are the highest throughput jobs I've had the opportunity to work on. We have multiple pipelines that the target for throughput is over 40 gigabytes per second for each pipeline. And this brings up all kinds of interesting technical hurdles. Also, another way to quantify that would be in terms of messages per second. I think this equates to a little bit north of about 70 million records per second that we're ingesting for each of these higher throughput pipelines. So again, the highest throughput things that I've worked on. So we do have multiple of these, and I have spent a bunch of time. I haven't been at Splunk all that long, but I've spent a bunch of time working on essentially this since I started. And the challenges that come up, the first thing is hey, I'm trying to go X speed and I can't go that fast. What's up? So I spent a lot of time profiling these very high performance jobs and trying to understand their behavior. And of course, that's always challenging in a distributed system like Flink. Um, you have to get very comfortable and familiar with your profiler of choice. I personally spend a lot of time using Workit. Others on the team, they like Async Profiler, which is a great tool as well. But kind of like, what did we run into? As we're trying to scale up, I think one of the biggest hurdles we've come across is just tons of GC pressure. So at some level, the GC, the garbage collector and the JVM is just not able to keep up with what we're throwing at it. And you can imagine with 70 million plus messages per second and then across the cluster, there's just lots of opportunity for object allocation in the application code. And we have spent a lot of time trying to reduce that. Sorry. So that is my baby monitor. Stop, please. Okay. My wife's taking care of that, so don't worry about it. Anyway, so yeah, tons of time optimizing away object allocation. The only advice I have there is like be data driven, understand like what the bottlenecks are, use your profiler. We've spent a ton of time on this and have made a lot of progress. And the other like very low hanging fruit, just like a really simple thing. One of the sources of a lot of extra work for no reason and a lot of garbage collection, a lot of GC pressure is Flink's own like output flusher thread. So just like lesson learned, if you're doing high throughput jobs and high scale jobs, just turn that thing off. So set buffer timeout to -1, I believe, which just turns off the output flusher, because that thread alone is actually responsible for generating tons of work and garbage that isn't necessary in these higher throughput jobs. So I would recommend turning that off. It's very low hanging fruit. We don't have a ton of time to get into a lot more technical detail. If you want to talk at the booth or whatever, I'd be happy to talk more about it. But yeah, there's lots of tuning to do here to make these jobs run like this. But the other interesting challenge that's a scale challenge is, at the end of the day, Splunk has thousands of customers that we want to bring this offering to. And in the high level architecture, you can see that like at the end of the day, that these customer pipelines are all Flink jobs. And we've made the choice to run each job as a Flink job cluster, so they're fully isolated from each other. I really don't think there's a lot of other sane choice in terms of running customer pipelines. Kind of in a multi-tenant way. You can't have them interfering with each other, so you really do need to achieve some isolation, and I think Flink job clusters are the way to go. But the challenge is, and the working number is, like, how do you run 20,000 Flink job clusters? That's a pretty huge challenge. Manageability, observability, reliability. In order to engineer systems like this, you can't spend the right way to think about it is you can't spend a ton of time on individual jobs. Sure, we've talked about we have some very high throughput jobs, and those are special, but we also have like, that's not the case for most jobs, but what is the case is there's the target is tens of thousands of them. And I think that this brings up a lot of really interesting engineering challenges, mostly unsolved, at least unsolved in my experience. There isn't like anything out of the box that's going to work for you. But the engineering goals are make all of these jobs totally self-tuning, totally auto-scaling, and just dead reliable. And by dead reliable, I mean, when a customer throws any pipeline they want at you, the system needs to at least be able to gracefully handle it. Even if it's too expensive with the resources available, it needs to not throw errors, not restart, just sort of reliably grind away. And that itself is quite a challenge. Like, how do you build systems that are just dead reliable and just at least grind away? So that's a whole set of interesting engineering challenges itself. So we have lots of work in this area. I think we're about out of time, but I just wanted to give the quick pitch here. Like, why did I come to Splunk, and why I think that if you're interested in stream space, you should consider it as well. I think, many streaming engineers work on platform teams. And, this is like maybe in the data organization within their company, and they don't often like get the opportunity to work directly on the customer facing product. Now that's not strictly true, of course, but, I've worked a lot kind of like on that platform side. And I'm very motivated by being like kind of more product driven. So I think the interesting opportunity at Splunk is with DSP, stream processing is the actual product. And I think that's just an amazing opportunity. So yeah, there's lots of opportunity for direct customer impact and lots of technical challenges. And I think, yeah, we're hiring people that have Flink experience. And we'd love for you to join us. I think we're out of time. Thank you.